Okay, hey Warner, how's it going? You are watching a video of a very depleted pre-calculus class. We're actually going to review something we started on Wednesday, okay? But it's good to go through the review again and make sure we all know it. Okay. Basically, what we're moving on to now, kind of the new stuff since after Christmas break. The first truly, really new stuff we're looking at is what are called trigonometric identities. Okay. There we go. All right. These are ways we could rewrite trigonometric functions. Okay, so that you can basically to write trigonometric functions from one way to another. Okay. So these are common relationships you find in trigonometry. They also all go back to, when it comes down to it, the unit circle and the whole y, x, and r thing, okay, that you get from that. So we'll refer back to that often, okay? The whole like sort of SOHCAHTOA parts of a right triangle. So in fact, I'm going to go ahead and start off, okay? There's the unit circle. There's my radius. That part's y. That part's x, okay? And from that, we get the basic 6 identities, the ones we've seen over and over again. Okay? The whole SOHCAHTOA. The sine of theta, there's theta, is equal to y. The cosine of theta is equal to x. The tangent of theta is equal to y divided by x. The cosecant of theta is equal to 1 over y. The secant of theta is equal to 1 over x. And the cotangent of theta is equal to x over y. Okay? Nothing out of the ordinary there. We saw that before. But those are your first trig identities, the first 6. Okay? The next one we've also seen before, and again it just comes from this. It's what are called the reciprocal identities. Okay? I'm always spelling reciprocal wrong, whatever. IDs. Okay? And again, we saw it. This is where we have relationships like the sine is equal to 1 over the cosecant. Okay? Things like that. Part of the reason why is because if you look at this, remember the sine is equal to y, cosecant is equal to 1 over y. So if I were to flip that, okay, I would get the sine back, right? But if I flip that, that means I'd also flip the cosecant, which would be get 1 over the cosecant. So it all comes back to that relationship, the fact that that's equal to y, that's equal to 1 over y. That also means that the cosecant of theta is equal to 1 over the sine of theta for the same reasoning. Okay, I could just replace that y with sine of theta and be done. So the reciprocal identities, again, we've seen these before. The sine of theta is equal to 1 over the cosecant of theta. Likewise, the cosecant of theta is equal to 1 over the sine of theta. Okay? Makes perfect sense, yep. Which means cosine is what?
1 over secant.
1 over secant. And secant must be then? 1 over cosine. And our last one, tangent would be?
1 over cotangent.
1 over cotangent. And so cotangent must be?
1 over tangent.
1 over tangent. Okay. So those are the reciprocal identities. Okay. Any questions there or how we get them? Super easy, those three. Those right there. Okay. Good. All right. Now, the next couple of sets of identities that we're going to see, okay, are all based off of, again, relationships you see or with things. So, for example, like how the tangent is equal to y over x. We're going to use that fact to create an identity, okay? And so our next set of identities, again, for reference, there's a little unit circle, right up, okay? This next set of identities are called the quotient identities. Okay? And the quotient identities, obviously, quotient means what? Something has to do, or I find a quotient, it has to do with what?
Division.
Division. So these are going to be ones involving division, okay? I'm going to start off with our tangent, okay? Our tangent of theta. Well, remember the tangent of theta, I can rewrite as y over x, okay? But what's y equal to?
Sine.
The sine of theta, right? And x is equal to the cosine of theta. So the tangent of theta can actually be rewritten as the sine of theta over the cosine of theta, okay? Again, because it's all back to sine is y, cosine is x, so it's just still y over x. We're just rewriting that tangent now in terms of something new, okay? That's okay. Come on by. Finished?
Yep.
Cool. Okay. How else can I write that then?
1 over cosecant over 1 over secant.
Yep, I can write it that way. 1 over cosecant over 1 over secant. But there's an easier way to represent that notion. It would just be secant over cosecant. Okay? Oops, theta, not x. Over cosecant of theta. Okay? And again, because that's just cleaning up what you just read out to me. Okay? So that's another way I can write that identity. So this is called a quotient identity, and we get the tangents. So if we do that to tangent, can we also do that to the cotangent? You bet. What do you think cotangent of theta is going to be?
Cosine divided by sine.
Good. Cosine theta divided by sine of theta. And if we're doing it in terms of secant and cosecant? Cosecant of theta
Yeah.
over secant of theta.
Sweet.
Da, 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 da. Okay, and so that's what's called a quotient identity. Okay, so if you solve a tangent in an equation and you want to get rid of it, you can just change it to sine over cosine, things like that. Okay, and in fact, later on when we're solving equations using trigonometry, that's oftentimes what we'll end up doing is we'll just say, I don't want this tangent here, let's get rid of it, right, in terms of sine and cosine. In fact, there's actually a method of doing solutions to these things where you say, everything except for sine and cosine is really hard to deal with, so let's just convert everything to sine and cosine. And you do that, and usually when you do that, everything just kind of becomes obvious and falls into place. So it's kind of like, we don't like difficult things, let's make it sine and cosine. But things like the quotient identities let you do so. Okay. So any questions about these right here? Nice and easy, there's only 2 of them. Okay. Alright, excellent. Okay. Our next set, okay, again, let's draw up our unit circle. And I'm drawing a really bad unit circle right here, but whatever. Okay. There's our little triangle. If I took that right triangle and looked at it, okay, how can I relate the sides to each other? For example, how would I get 1 from y and x? I would do what?
Squared plus
Square, right? Pythagorean theorem, right?
Yeah.
So from this I can get then that x squared plus y squared. Actually, let's make that y squared plus x squared. There's reasons for that here in a second. Would be equal to 1 squared, which is 1. Okay? That's our Pythagorean theorem. Okay? But again, what can I do with y and what can I do with x? I can replace them with what? Sine and cosine. So the y squared plus x squared equals 1. I can turn into the sine squared of theta plus the cosine squared of theta is equal to 1. That's called a Pythagorean identity. Thank you, Pythagoras. Like, actually, I can tell some fun stories about Pythagoras, but we'll do that after we're done. So sine squared of theta plus cosine squared of theta is equal to 1. Okay? Now, from this identity right here, I can get 2 others by just manipulating around parts of this equation right here. Okay? So the first one I could get is if I divide both sides of the equation by the sine squared of theta. Okay? So if I had the sine squared of theta plus cosine squared of theta equals 1, and I divide it by the sine squared of theta, everything gets divided by sine squared of theta. Okay? What happens to that right there? It becomes 1. What would that become? Cosine over sine is what?
Tangent. No,
Not tangent.
Cotangent.
Cotangent. Okay? The fact that they're squared just means I would square the cotangent. Okay? So cosine squared over sine squared would just be cotangent squared. Okay? So we get the cotangent squared of theta. And then what's 1 over the sine equal to?
Cosecant.
Cosecant.
Wow.
Just because it's sine squared doesn't change anything, it'll just make it cosecant squared. Okay? And so that's our second Pythagorean identity, is that 1 plus the cotangent squared of theta is equal to the cosecant squared of theta. Okay? Again, falling in line with these right here. By the way, too, whenever you have one of these identities, especially things like the Pythagorean identity, realize I can rewrite them tons of different ways. This is just what they're commonly rewritten to as. But if I need to do a manipulation, I certainly could. For example, this guy down here I could rewrite as 1 equals the cosecant squared minus the cotangent squared. Okay? And that might pop up. So I might, if I see cosecant squared and cotangent squared in the problem, I'm like, well, what can I do with them? See if you can't rewrite them to be like this right here. Okay? Same thing goes right here. I can say the cosine squared of theta is equal to 1 minus the sine squared of theta. Okay? Again, all I'm doing is just manipulating this equation up here. So don't take it that these are the only ways I can use these things, or these are the only switches I can make. You can make the switches and then, even with what you're given, manipulate them as is. Okay? All right, that brings us to our next Pythagorean identity. I'm going to rewrite this, in fact, as cosine plus sine instead. I can do that. There's nothing preventing me from doing so. It's equal to the same thing. Good old commutativity. Okay? So, what do you think I'm going to do here? So the first one I divide by the sine, so this one I think I'm going to divide by the cosine. Good. So we'll divide this by cosine squared of theta. Divide this by the cosine squared of theta, which means we have to divide this by the cosine squared of theta. So what does everything come out to be? This right here becomes 1. Sine over cosine is? Tangent. So tangent squared of theta. And 1 over cosine becomes? Secant. So secant squared of theta. And we've got another Pythagorean identity. So our 3 Pythagorean identities, there's our first one, second one, third one. Okay? And there you have it. Okay? So that gives us basic, reciprocal, quotient, and Pythagorean identities today. Okay? And those are the 4 basic, or 4 what are called fundamental identities. Okay? Now, there's 2 other ones I can add on here today, but they're a little different. They don't have to deal with a manipulation like this. They have to deal with more of what goes on with the angle part of the thing. And it just so happens it comes back to how the graphs of these things work. Okay? So, the first set we're going to look at are generally referred to as, I believe they're, I always forget their name. They're about, to be honest with you, they're not used all that much. Co-function identities, that's right. Okay. Okay, so co-function identities. Okay. Okay. Now, this group of identities, these have to do with a manipulation of the angle part of the sine, cosine, tangent, etc. Okay. It all comes back to graphs. Okay. As a quick reminder, okay. Reminder of graphs. Okay. This is the sine graph, and I'm not going to label things. I'm just going to draw them. Okay. And there's my cosine graph. Okay. What's the difference between these two? The cosine's been what? Been yanked back, it's been nudged over, or I could say the sign's been nudged over, any way you want to look at it. So it's the same picture, it's just there's a difference in phase, okay? Slight difference there in phase, okay? And the difference in phase is precisely pi over 2 in phase. So I can write an identity up saying that the sine, I could say my sine, if I want to make it equal to the cosine, I would do pi over 2 minus my, my x. That would give me the cosine of x, okay? Because what I'm doing there is I'm saying, okay, if I rewrote this, that'd be minus x plus pi over 2. So that means I'm going to, when I flip the signs around correctly, that means I'm going to yank this thing back pi over 2 this way. Well, what would that do to that top? Put it right where the cosine starts, okay?
Should we
So-
use x there or theta?
I'm sorry?
Should we
X or
use-
theta doesn't
yeah.
matter, okay? Just likewise, actually, with any of the identities, it actually doesn't matter what the variable is behind it. It's just, as long as it's the same variable, obviously. And in fact, we're going to see some, you'll see in the book they use things like U's, they use things like W's, they use things like V's, etc. They'll even use numbers at times, okay, and actually tell you what the angle is, but you're still able to rewrite it, okay? So, my cosine graph here, I could also write it as the sine of pi over 2 minus x, okay? So what do you think that means I can write my sine graph as?
X plus pi.
Okay, in terms of cosine, would it be the same exact thing?
Yeah, cosine.
Yeah, it'd be the cosine of pi over 2 minus x. That's also what the sine of x is equal to.
Should
And
I
again,
plus?
it's saying, well, no, because again, if you clean this up,
Yeah.
okay,
Yeah.
again, it's saying we're yanking this thing over in the direction we want it to be, okay? So those are two cofunction identities, okay? What do you think that means for secant and cosecant? What did the secant cosecant graphs look like? Weren't they basically based off of this here? Didn't they have all the same properties and pieces? Absolutely they did. Okay. That's a representation. Here's my cosecant. Okay. So I could probably rewrite that in terms of the secant, and in fact I could do it the same exact way as I did before. Okay? By using that cofunction identity. Okay? Likewise, my secant graph, which would sad ghost face graph. See what I mean now? Sad ghost. Oh, poor little sad ghost. Anyway, that's my secant graph here. I can rewrite it in terms of the cosecant by simply doing the same exact thing I've been doing with the others. So cosecant of pi over 2 minus x equals the secant of x, okay? By the way, another way I can confirm these, I can also draw a unit circle and show you how they all will match up on that unit circle, okay? Perfectly, okay? And so, if you do these manipulations, which is very helpful, okay? Makes life easy for us, okay? Excellent, okay. What do you think is going to happen with tangent and cotangent? Do you think they're going to do anything different? Nope. They're also going to follow the same way, okay? Now, with the tangent and cotangent, okay, so the tangent of theta, or x, we'll make it x, to keep it in line with the rest of them, okay? We could write that as the cotangent of pi over 2 minus x. These are a little bit more difficult to see exactly because, remember the tangent graph, okay, looks like this right here, okay? This would be the tangent of x. But the cotangent graph, same sort of picture, but it's been what? It's been flipped, right? So you would say, oh wait, there must be a minus sign shift there, okay? Because we're usually, when we flip things, we just throw a minus sign out front. In this case, no. If you go back to the unit circle, okay, and look at the quadrants in which these things work on, and actually look at the numbers in them, okay, you will see quite quickly that it works out just fine. In fact, what's happening here is, if I do this shift on it, okay, to the cotangent, like it's written out here, okay, what happens is, this part rotates around to be right here, and this part rotates around to be right there. It just gives you the tangent, okay? So that also means, though, I can do the same thing. So my cotangent over here, I can rewrite that as the tangent of pi over 2 minus x. And again, if you look at the unit circle and actually do what it says, it's like the angle, that's the picture you'll get, okay, when you graph it out. So they indeed work out nicely that way, okay? Any questions about that? All right, excellent, good. Okay. So those are your cofunction identities. Again, those are kind of graphing identities. The last set of the graphing identities we're going to look at, okay, are called the even and odd identities. And these aren't even really identities, okay? They're always listed in groups with the rest of the identities, but in reality, they're just properties of the functions themselves. Okay, remember sine of x is a function, cosine of x is a function, etc. Okay, and what they're basically saying here is it goes back to what even and odd means in terms of functions. What does even mean? It's got what? Symmetry about the what?
X-axis. No, y-axis.
Y-axis, right? So it means that if I held it up to a mirror, the pictures would be the same. Okay. Likewise, odd means it has symmetry about what?
X-axis.
Not x-axis, but you had 3 types of symmetry: y-based, x-based, and diagonal, or about the origin. Okay, odd's about the origin. There's only one type of function that has symmetry about the x-axis. Okay, and that's the function y equals 0. Okay. Because remember, otherwise, if we flipped it around the x-axis, we'd fail the multiple line test. Or, sorry, vertical line test. Multiple line test. The vertical line test. Okay? So yeah, that's taken way back from like the first week of September, what it means to be even and odd. Okay? But even and odd applies to our functions as well. Okay? And so, if you would actually look at the graphs of these things, or actually look them out, or compare them on the unit circle, you discover that, remember, even means that if I put in negative x, I get the same, or even means if I put in negative x, I get the same answer out, okay? So if I said like, f of negative x is equal to f of x, okay? And odd means if I put negative in, okay, I get the negative answer out, okay? And if you think about our graphs here, let's go back to sine and cosine, okay? Sine, is that going to be, if I were to mirror it, if I made my x's negative, okay, what's going to happen? It's going to flip down over here, right?
Yeah.
So it's going to be an odd function. Yeah. Cosine, though, if I flip my x's, it's going to be the same picture, right? So it's a even function. And so even and odd, we could actually group them. Our odd ones over here, looks like up, but whatever. Let's get rid of that. And even, okay? So as we saw from looking at the graph, sine of x is odd. That means that the sine of negative x is equal to negative sine of x, okay?
Sine of asterisk.
Okay, sine of asterisk. Is that what that looks like? Oh well. Sine of negative x is equal to negative sine of x, okay? But it also means that the cosine of negative x is equal to the cosine of x. There's no change there, okay? So if you negate the angle, nothing changes to the cosine. Okay, it would be the same. You negate the angle for the sine, it flips upside down. Okay, that's what it would mean. So odd or even. So if the sine is odd and the cosine is even, what do you think about the cosecant and secant? What would the cosecant be? The cosecant is the what to the sine? Reciprocal, right?
Yeah.
So that means cosecant should also be odd. And that's indeed the case. The cosecant of x, of negative x, would be equal to negative cosecant of x. And again, if I went back to the picture, you would see it. Oh wait, if I negate my x's, the thing would flip about the origin. Okay? So what does that mean about the secant? It is even. Okay? Again, follows along the cosine. It would be an even function. Okay? Alright. That leaves us with our last two, tangent and cotangent. Okay? The tangent is already what about? Okay, if I drew the picture of the tangent, actually let's just go back one. What does that already clearly have?
Oh, symmetry.
Symmetry about the
Origin.
origin, which means automatically, what do you think the tangent would be? Odd. I don't even need to bother to test it. I know it's going to be odd. You just look at the picture of it, and it's clearly an odd function. Okay, so the tangent of minus x must be equal to the negative, the tangent of x. Okay, now cotangent is a little bit trickier. Oh, don't need that. That's calculus. Okay, cotangent is a little bit trickier to see exactly, but what if I were to move that cotangent to the origin? What would it look like? What would it have symmetry about again?
The origin.
The origin. It has origin-based symmetry again. So if I nudge it over, I can clearly see it has origin-based symmetry, which means the cotangent must also be what? Odd. Okay. Not even. It's odd. It's an odd function. Odd function. Okay. But there you have it. Okay. So yeah, the only two ones that are even are cosine and secant. The rest are all odd. Okay. There's the groupings of them. Again, it goes back to the whole notion of an odd and even function. They're called IDs. Really, I mean, it's just a straight-up property of the function. So you don't really have to. I mean, these you could just graph them and clearly see which ones are odd and which ones are even. So it's not like it's really that big of an ID. Okay. I will tell you this right now, kind of in the exercises and the things we do. The graphing identities, so the even and odd identities and the cofunction identities, we hardly ever use. Okay. So it's useful to know what they are, but quite frankly, because we know how to graph these things, we can generally figure them out without necessarily needing to use them. And of those identities, the cofunction ones are going to be the more useful of the two, because it's simply telling us how I can change a sine into a cosine if I need to. Okay. The other identities, reciprocal, quotient, and Pythagorean, all those happen all the time. Okay. They happen when you're doing problems involving trigonometry. Okay. In fact, let's take a look at a few examples of how identities work. How to use identities. Okay. So basically, what you do with these things is essentially a lot of times you're using them to either simplify a function down or rewrite something so that it's equal to something else. Okay. So for example, a common one might be something like simplify. Okay. The sine of x cosine squared of x minus sine of x. Okay. And what we're going to be after doing here, okay, is generally speaking, when you see simplify, and usually the directions are very, very clear cut on this. They want this to get down to as few trigonometric functions as possible. Okay. Right now, I've got two. I've got a sine and a cosine, and I've actually got, in that regard, three distinct parts: sine here, cosine here, and a minus the sine there. Okay. So I want to see if I can't get this down to just one thing. Okay. And this is where identities come into play. Okay. So first, what can I obviously do? I can do what to both parts of that? They both have a what? A what?
By sign.
I can divide by sign, but I can also just pull it out, right? Just factor the sign. Let's start there. Okay. So we factor out our sign. Okay. So factor sign. Okay. All right. So far, so good. Okay. Now we've got our sine out here in front and a cosine squared x minus 1. Oh boy! When I see something like cosine squared of x minus 1, what immediately should I think of?
Years. No, I'm kidding. It being symmetrical at the origin.
Okay, actually it would be symmetrical if you, not about the y-axis,
About the
but we
y-axis.
don't need to worry about that.
Pythagorean.
A Pythagorean identity, right? We have a cosine squared. Okay, only time we saw that was with Pythagorean identity.
Yeah.
Now our Pythagorean identity, if I go back to that slide,
Oh, it's
Okay.
sine, yeah.
okay, is, one more, Jesus, okay, is sine squared theta plus cosine squared theta equals 1. I have cosine squared theta minus 1. So what do you think that's going to be equal to?
Sine squared theta.
Okay, so it should be sine squared theta, but the signs are wrong, right?
Oh, yeah.
It would be 1 minus cosine squared of theta equals sine squared of theta. So if my signs are wrong, what does that just mean for my sine squared of theta? It would be what? Its sign would be what? Flipped. It'd just be negative instead. Okay? And so we can notice that. We can basically say cosine squared of x minus 1 is a Pythagorean one, or is based from a Pythagorean identity. So let's rewrite it. Okay? And the rewrite of this thing is, again, we can recognize, wait a minute, that's like 1 minus the cosine squared of x, which would be sine squared of x, but our signs are flipped, so it must flip the signs. So this thing would become the sine of x times negative the sine squared of x. Okay? And see what I mean before when I say identities, sometimes you have to like rewrite them or finagle them a little bit. Case right here. Okay, well we're trying to get this down to one identity. Are we almost there? You bet. What's sine of x times negative sine squared of x?
Negative sine cubic, right?
Yeah, negative sine of x cubed. Okay, so we've simplified it. We've gotten it down to just one trig identity, okay, or just one trig piece. So I can come up here from the very beginning here and say this thing right here is just equal to minus the sine cubed of x, okay, and be done. Okay, so that's one example of how you use trig IDs. Okay. Another example, okay, of using trig IDs is essentially, okay, basically proving another use. Okay, proving two sides are equal. Now, when I say the word prove, okay, most of you are probably shuddering right now and thinking back to geometry and then new proofs of geometry. Don't worry, these are nothing like that, okay? You're not going to go through those steps. You're not doing like a double side, the two-step or two-side, or whatever the heck they like to call it this month, proof, okay? Instead, all you're doing, okay, is basically just showing through trigonometric properties how side B, or how one side is equal to the other side. Okay? So, an example of this, a few examples here. One, okay, will be this one right here. So we've got 30, this is 39 for the textbook. Okay? And it's that the sine of theta plus the cosine of theta, okay, cotangent of theta, okay, is equal to the cosecant of theta, okay? And so what we do here is, basically, we're just trying to manipulate this thing so the two sides are equal, okay? And both sides are fair game, okay? You could just play around with both sides to get what you need to, okay? So, let's kind of start off. I've got everything, there's like a multi-step process involved here if you have trouble with doing things, okay? But one of the easiest ways to approach these things is to say, okay, I want to get rid of as many of these things as possible, okay? And so what I want to do is, I've got, for example, a cotangent and a cosecant, okay? I don't like the cotangent, and I really don't like the cosecant, okay? And as you get further along in math, you too will learn to hate the cotangent and really hate the cosecant, okay? So, let's get rid of them. How could I get rid of them? What could I do?
Cosine over tangent.
I could turn the cotangent to cosine over sine, okay? And the cosecant can become what?
Sine.
1 over sine, right?
Oh, yeah, yeah.
So we use basically, if I wanted to write all the steps, and when you first get used to this, it might be useful to do. It's just, but I can come up here and say use, okay, use the quotient ID
Pythagorean.
on the cotangent and reciprocal ID on the cosecant. Okay? So what happens? Sine of theta would be plus the cosine of theta over sine of theta. Okay? Like so. And that's going to be equal to 1 over the sine of theta. So hey, I've just gotten rid of all those, the cotangent and the really stupid cosecant.
Good
Okay. And now it turns sines and cosines, which are much easier to work with, right?
Yeah.
Okay. Well, we're doing things algebraically. So the next thing I'm going to do is I'm going to multiply this out here, make it cosine squared. This sine, though, I'm going to add it to this, which means I need a common denominator, right? What's my common denominator? What's my common denominator going to be? Sine. Okay, so let's go ahead and do that. So this sine here would become sine squared of theta over sine of theta, right?
Yep.
Plus cosine squared theta over sine of theta is equal to 1 over sine of theta, which gives me then that the sine squared of theta plus the cosine squared of theta over the sine of theta is equal to 1 over the sine of theta. And, oh wait, what's sine squared plus cosine squared?
Oh.
It's the, just did it the previous problem, y squared plus x squared. What's that going to be equal to? 1. It's a Pythagorean identity again.
Oh.
Okay? Pythagoras spaghetti.
Pythagoras was the man.
Pythagoras was a crazy cult leader. Yes,
So he was the man.
sure. If you think,
The man of the cult.
Was this like the cult of the triangles?
yeah, he made a cult of mathematics.
Were they radical? Did they kill people for their ideals?
They